again. Thank you very much. All right. So, when I was a kid, I bought a microscope, really cheap microscope, but it was so impressive. I could see things that you can't see with your eye, like under the microscope, there were these little tiny little beautiful things like hair of little animals, that was just beautiful little hairs, colorful and stuff. I was really impressed. But then I got a cheap telescope and I was even more impressed. I could see the craters on the moon. It's just like you travel someplace, like you travel, at least in your mind, when you look at the moon and you see the craters and the mountains and stuff, it's just like traveling there, like you're orbiting the moon. And so my telescopes have been getting better and bigger ever since. I remember my dad took me at 9 o'clock at night to buy my first quality telescopes from Japan. And that was $200 back then. That was a lot of money. He spent, I think, half an hour trying to talk the guy into bringing it down from $200 to like $190, $180. I was so embarrassed. But I was like, 12 years old or 13 years old. I didn't have any say. But when I took it home and I looked at Saturn through that telescope, that was it, man. I just fell in love with my telescope. So I've been carrying my telescope around ever since. I'm 67 years old. I've had my telescope when I was 13 years old. But I tell you one thing, telescopes are actually gotten cheaper since then, which is amazing because I remember my uncle had a $10,000 house at Venice in California. And that $10,000 house is going for $1 million now. So everything has gotten 100 times more expensive. Telescopes have gotten less expensive because the Chinese have learned to make really quality, cheap telescopes, and the market is flooded. If you think the US is making any telescopes for people, you'd be mistaken. All the telescopes are made in China. But they could also be, they bought all the American companies too, so they're really into telescopes as well. So I like that. I like the fact that telescopes are so much cheaper. So if you have any questions to ask me about telescopes, binoculars, optical things of any kind, since I've built so many telescopes in my life, I'd be more than happy to answer you. All right, so let's see what we got here. Now, the first thing we're going to talk about is the prism, just a simple prism, right? Now, you've all seen a prism like in your chandelier at home or some kind of a cut glass. You can see when the white light goes through it, it becomes this beautiful, colorful thing that you see on your wall, right? You see the reds, oranges, yellows, greens, blues, indigo and violet. And to me, blue, indigo, and violet, they're almost the same color, to me. So why is it that when light enters a prism, it bends? So you can see the white light is going this way. Now it's going this way, so it bent. You see, it's bent. And then after it bends, it becomes this beautiful rainbow of colors. Why is that, right? Well, two reasons. One is we call this prism a medium. Medium is, like normally you see a medium is some gypsy or something sitting behind a big globe, and she touches it and she says, I'm talking to your grandfather, he passed away 10,000 years ago, right? That's a medium. That's an in-between, right? So that's what a medium is. It's in between. Now, light, when it travels in space, it travels at the speed of light. So when you hear somebody say, speed of light is a constant, speed of light is a constant in vacuum, in the absence of air, because air also acts as a prism, right? So in other words, air itself, when the light goes through it, it bends. Light bends. So when you look at the sun at sunset, the sun is already set. What you're looking at is what is called a refracted image of the sun, right? So everything is bending. You can see this if you put a little spoon in a glass, you can see the bending of the spoon. So it bends because it slows down. The speed of light slows down when it goes through a medium. Again, that medium can be water, glass, plastic, air, and such. Any kind of liquid. Now, why does it become all these beautiful colors? Because when it bends, not all colors bends the same. As you can see, red is bending a lot less, whereas violet bends the most. And so that's why they spread out. Their speeds change. Red changes the least, orange a little more, yellow more than orange, green more than red, and so on. That's why they spread out. So that's why we get these colors, and that's why it bends. So bending is because of the speed of light decreasing, and then the colors, because each one of the colors bends a little differently. So they separate. All right. Okay. So what is a telescope then? Well, telescopes can be reflective telescopes, refractive telescopes, and also you can have telescopes that are very specialized, like radio telescopes, like X-ray telescopes, like gamma ray telescopes. Those are all very specialized telescopes that do not use the same thing as refraction of light and reflection of light to bring light into focus. So let's take a look at the refraction or refracting telescope. So if you look at the lens, a simple lens here, you can see light is coming in, and this light is parallel beams of light. You see, none of these lights are crisscrossing, they're all parallel. So if some object is emitting light, and this light is very far away for your eyes, let's say at infinity, like the light of the sun or the moon, infinity is something like more than 500 feet away. That'll be infinity for our eyes. They come together here and they focus. And so if you look here, every one of these little pieces of glass here is like a prism. So really a lens is like a whole bunch of little prisms end to end, just like that. So it's doing exactly the same thing that the lens is doing. Oh, I'm sorry, it's just doing the same thing that a prism is doing, except you have a shape that is like this. Right? That's called refraction. Refraction. Now here's the light again. White light is coming in, hits the lens, and it bends, and it becomes different colors. So a lens also produces these beautiful colors, except when we look at these beautiful colors, it's not so beautiful because, say we're looking at the moon, and the moon is all colorful. You don't want a colorful moon. That's a very low quality telescope. That's my first telescope that I built myself. Not good. So we call this chromatic aberration because the lens, a single lens, acts just like a prism. It refracts the light, refracts the blue light more so than red light. So red and green and blue and all that, they separate, they come to a focus, but at different distances. So the red light focuses the farthest out, away from the lens, the green a little less, blue a little less. So you see those fake colors. This is called chromatic. Chroma means color in Latin. Chromatic aberration is this colorful problem that all lenses seem to have, especially single lenses. Now, if I get two lenses, I can fix that. But in they just figured this out in the 18th century. So in 16th, 17th century, they had a problem with this chromatic aberration. They made the distance between the lens and where they looked at the image greater, and that decreased the chromatic aberration. So if you look at something like this, you have to respect this. These guys went through hell to get an image. I mean, it's so difficult. I can't even explain to you right now how difficult it is. Because first of all, if you have a long telescope like that, you have to mount it like on a tripod. There's no tripod big enough to mount something like this. So they had to build this to mount this tube or a telescope. Incredibly difficult. I mean, it's magicians back then. I don't even know how they did it. So now, if you use two lenses that refract the light a little differently, and they're made specifically to correct for this red and the blue and the green problem, the chromatic aberration, we can fix the chromatic aberration. One glass is very soft, it's called crown. One is very hard, it's called flint. And they both refract the light a little differently. So we call these lenses, the two of them together, we call them the achromatic lens. So an achromatic lens is made out of two separate lenses. Normally they either glue it together or there's some space in between them. It's called air-spaced. So these air-spaced lenses, they bring the red and the blue together in the same place. What we call the focal point or the focus point of the lens. The distance between the lens and where the image is focused is called the focal length of the lens. So all lenses have a focal length. Now, there's two different shapes for a lens, and I'm going to draw all this out for you. One is called convex, and this crown glass has got one surface here that is convex. The achromatic lens has actually four surfaces. So if you see this light blue lens, it's got two surfaces here. They're both convex. Then it's got a flint glass. One side is flat here. The other side is concave. It's like caves in. I'll write that on the board for you. You don't have to worry about it. So we have a focus point, a distance between the lens and where the image is focused. The focus point or the focal point, that distance is called a focal length. Important. Focal length is very important. What we call a refracting telescope most of the time has not just one lens, but it has two lenses. So you have an achromatic telescope. If you buy a single lens, you're going to get that chromatic aberration. I don't even think they sell single lens telescopes anymore commercially. Light comes in as parallel beams of light from infinity. Say this galaxy here, light is coming in. It gets focused here. So that distance is called the focal point of the objective. This lens in the front is called the objective lens. It's the one that collects the light. Objective. All right, so it brings the light into a focus. It collects the light and brings it to a focus. And here you need a second lens to see this image. The second lens is a magnifier. This magnifier is also referred to as an eyepiece. So you have an objective lens and an eyepiece. All lenses have focal lengths. Focal length of the objective is very long. Focal length of the eyepiece is very short. Together they magnify the objects so you can see an image. So now for further information, please allow me to stop sharing. Get the second. Okay. All right, so let me get up there, you guys. Okay. First of all, let's talk about that convex and concave. So convex is like this. This is a convex shape. Convex shape. Convex. And this would be a concave shape. The mirror that you look at your face in the morning to put your makeup on. I have one every day. I got one from Costco. It's a big one with a light around there, right? That one is a concave shape. So you can see your face nicely in a concave shape. So this is a concave. Kind of like it caves inward. Since there's only convex and concave, if you just remember the concave caves in, you should remember it. Concave. Right? All right, so let's have a lens here. Here's our lens. And we'll pretend that there's no chromatic aberration. We already know chromatic aberration gives you extra color and it ruins the image. So here we have beams of light that are parallel coming in. And then they get focused here. and we said this is called an objective lens. There's your objective lens. It brings a light to a focus. It bends it through what we call refraction. So this is the refracting telescope. Refracting telescope, right? Uses refraction, bending of light to produce an image. So here we're going to get a second lens. Second lens is much smaller, and its focal length is much shorter. I'm going to draw both of them so you can see later. So this is called an eyepiece. An eyepiece is a magnifier. A magnifier. So old people like me, they need a magnifier to read the fine print in the newspaper. You've seen that. So what's the difference between a magnifier, this eyepiece, and the objective? Well, this is the only way, by the way, that you can see an image here. Here's your eyeball. So the eyeball is looking through the eyepiece, and then you're looking at what we call the focal point. This is called a focal point, or you can call it the focus point. We use a different color. Let me say this is the focus point.
I have a question.
Yeah.
Is the eyepiece convex or concave?
Well, actually, there's both. They're not that simple. They have multiple lenses. So I'll show you one that is kind of complex, and I'll show you one that is very simple. This is like an eyepiece here. And it says so. It says like what kind of eyepiece it is. It's a colossal eyepiece. It also says, if I do this, maybe it focuses a little better. And it's got the focal length in here. It says 20 millimeters. See that? 20 millimeters. So that's just the lens. If I shine the light, it focuses about 20 millimeter behind it. So that's like this. You see how close to my body it is? Very, very short distance. The image is focused. So very short focal length for this lens here. Whereas this is like an objective lens. So the objective lens focuses much, much farther. See, it's many, many, many inches away. So the objective has a much longer focal length. The eyepiece has a very shorter focal length. And so for that reason, you can't really say, is it convex or concave? Because they use multiple lenses, and some of those lenses could be concave, some could be convex, just like you saw in the achromatic lens, right?
Professor, I have a question.
Yeah.
The left portrait, the left sketch that you did, you said was a refracting.
Yeah, these are all refracting telescopes. We haven't gone.
Right. And then you added the eyepiece magnifier. That makes it a different kind of telescope. That makes it the
this is still a refracting telescope. So
sorry.
It's a refracting telescope.
Right.
Refracting telescope.
All of this together is a refracting telescope.
That's right. So a refracting telescope requires two lenses, minimum two lenses, especially if you want to see. Now, if you don't want to see anything, all you can do is to put your camera here. If you put your camera, you don't need an eyepiece. You just have a camera and you have the image focused on the camera detector, right? So a refracting telescope that is visual, a visual refracting telescope needs the eyepiece. If you don't want to see anything, if you just want to take a picture, then you just need the lens up front. You need the objective. You follow? All right.
Yes, and that's a picture of an eye looking through the lens, correct?
That's correct.
Okay, thank you.
Yes, that's my eye, actually. Just kidding.
Ah, nice eye.
Yeah, that's right. All right.
Could I ask a question about taking a photo? So If we get a telescope, do we need to remove the eyepiece to take the photo?
Well, if you do, you're going to get a much better picture. If you don't, then the image is going to be not so hot. So
Okay.
there's different ways of doing it. One is called afocal. That's with the eyepiece in. And if your eyepiece is not removable, then if you're
Right.
stuck with it, you can still stick the telescope behind, camera behind the eyepiece. It's possible. But your best, sharpest images are without the eyepiece. Yeah. All right, so
Okay.
now let's take a look at these two lenses. The objective. This is the objective lens. Has a very long focal length. Longer than the eyepiece anyways. So it focuses way down there. The distance between this objective and where the image is focused, this is called focal length. So the objective has a long focal length, whereas the magnifier has a very short focal length. So this is the eyepiece. Eyepiece has a very, very curvy surface, and it focuses almost immediately behind here. So it's a very short, this is a very short focal length. So you need a minimum of two lenses to have a visual refracting telescope. One to collect the light and bring it to focus, right? One to magnify this image at the focus. So just like you magnify an image, you have an image in the telescope. Inside the telescope, there's an image. So you use the magnifier to magnify that image, okay? And so that's one of the jobs of a telescope, is to magnify. So if you look at the moon, how many times you magnify the moon is the magnification power of your telescope. So what does that mean, magnification? Let's take a look at that. I'm going to erase this. Is that all right, you guys? Can I erase this picture?
Yes, I just need the right side.
Okay, good. Right.
I have a quick question.
Yeah.
Does the objective lens and the eyepiece kind of do the same thing, but just at different at different magnitudes?
No, one of them has got a long focal length, and you can't really use it for magnifying things. Because if I'm looking at something and say, this is an objective, all right? So if I want to magnify something, like let's say I want to magnify these, it won't really do it. I don't know, you guys can't really see this. Can you see this? It's not a very good magnifier. Can you see my finger here being magnified? You know, this is not a very good magnifier. But so objective has a long focal length, and the magnifier has a very short focal length. So
Yes, sir, I have a question too.
you need both of them. You need one to bring the light into a focus, second one to magnify that image. Yeah, please.
Why is it that the objective has a longer focal length? Besides it, is it just that the lens is bigger?
Well, give me a second here. See what this magnification is all about. How many times you
Professor,
magnify
You
has to
said,
do with
sorry, you said one lens to bring it into focus, one lens to what?
magnify.
Matt, thank you.
You're welcome. All right, so let's see what this magnification formula is. Very simple. Magnification is equal to the focal length of objective divided by the focal length of the eyepiece. That's why you need the focal length of the objective to be longer. If the focal length of the eyepiece is longer than the objective, you're going to demagnify. You're going to make it smaller. It's like looking through a telescope the wrong way. Like if you turn your binoculars around and you look at somebody, they appear to be farther, not closer. So focal length of the eyepiece. like that. So that's the formula. I'll rewrite it for you so you can see it a little easier. Magnification is equal to focal length of the objective divided by the focal length of the eyepiece. That's it. Focal length of the objective divided by the focal length of the eyepiece. So your objective has to have a longer focal length than your eyepiece. Your eyepiece needs to be shorter focal length. And when you use a telescope, you also have to focus the telescope. Why do you have to focus the telescope? Because everybody's eyes are just a little bit different. That's why you need to focus. So the objective is this guy right here. Now there's the objective. This is the eyepiece here. So when I look through the eyepiece, I need to move the eyepiece forward so I can make the image nice and sharp. If you don't make it nice and sharp, you're going to have a fuzzy image, right? So you have to make the eyepiece a little farther out, a little closer. And normally you use a focuser. So a focuser moves the eyepiece forwards and backwards until you get a nice, sharp image.
Do you wear glasses when you're doing it, or do you take them off to look through a telescope?
It depends. It depends because glasses can have astigmatism.
Mm-hmm.
If your eye has astigmatism, then you need to use your eyes, your glasses.
Gotcha.
If you don't have astigmatism, then yeah. But the glasses are never a good thing when you use optical instruments of any kind.
Yeah.
So when you do have stigmatism, you need to keep your glasses on. If you
That's right.
don't take
That
them off. Okay.
Right.
Because I was trying to look at the Christmas star, what they were calling it.
Uh-huh.
Remember when Jupiter and Saturn aligned? I was trying to look at that through my binoculars, and it was hard to see, and I took my glasses off, and but these are binoculars, not a telescope. So, but
binoculars are actually telescopes.
oh yes,
They're just two telescopes.
two of them.
You got two telescopes, right? You got two one side. In fact, I'm going to talk about binoculars in just a second.
I always find it hard to focus, and so I have wondered exactly what Linda queried was, do I take glasses off or not?
Did you take your glasses off or you kept it on?
I did both, but it turned out I was looking at the wrong object in this. And then all of a sudden I could see it because I thought what I was looking for, I thought it was a helicopter. It was so bright and clear that you could see it with your bare eyes. It was amazing.
Wow.
I thought it was a helicopter the whole time.
Good one. That's a good one.
Sorry, I have one more question.
Yeah.
What is better for what situation, like refracting lens versus a objective lens? What would you use each one for?
Refracting lens and objective lens are the same thing.
But all right, then can you remind me what the differences are then? Because
No, it's the same. There's no difference. An objective lens is a refracting lens.
now I'm confused.
Lens, it's just a lens. What it needs to do, its job is to collect the light and bring it to a focus. That's all. So the light is coming in, it grabs the light and brings it to a focus. That's all it does. It gets the light, bends the light, and brings it to a focus. That's all it does. That's what the
Then
objective lens are.
Magnifier is short focal length and an objective is long focal length.
Correct.
Okay.
Now, when you divide those two numbers, the focal length of the objective and the focal length of the eyepiece, that determines magnification. So let's see now, if I have the distance between the objective and the focus here, say 100 inches, all right? 100 inches is the focal length of the objective. And I want to magnify 100 times. I need to use an eyepiece that has a focal length of 1 inch. If I take a 1-inch eyepiece with a 100-inch focal length objective, what do I get? So I have 100 inches, I divide it by 1 inch, I get 100 magnification. Magnification is written like this, X. That means times. So you magnified 100 times. You brought something closer 100 times. or you made it bigger 100 times. So you look at the moon, and the moon to you maybe looks like this, and you make it this big. So you just magnified it 100 times like that. That's one of the things a telescope does. It magnifies. Now, I want to magnify 200 times. What do? So now I change my eyepiece. So you don't just have one eyepiece for every telescope, you need 5 or 6 eyepieces. Although if you have a pair of binoculars, the eyepieces are fixed. They're glued in there, so you can't really change that. With a telescope though, you can change anything you want. You can change the magnification according to the eyepiece. So shorter focal length eyepieces, like a 1/2 inch, will give you more magnification. So if I have 100-inch focal length telescope lens or an objective, then I get a 0.5 inch, a 1/2 inch eyepiece. This gives me 200 times magnification. There is no units here, right? Why isn't there a unit, by the way? Well, look, you say 100 inches divided by, let's say, 0.5 inches. Now, when you divide 100 inches by 0.5 inches, just remember this, not just for this class, for any class that you ever take, or whatever, calculations you'll ever do in your life. The units also simplify. So there's inches on top, inches on the bottom, inches, inches. 100 divided 0.5 gives you 200, and there's no unit because your units just got canceled out. So your units can be canceled, all right? So magnification doesn't have a unit. This X means times. 200 times. All right, so I want to magnify 50 times. What focal length eyepiece do I need to magnify 50 times?
2 inches.
25?
2 inches, that's right, 2 inches. So magnification then is equal to 100 again. You only got one objective lens. They're very expensive. When you buy a telescope, you get one objective lens, but you get many eyepieces. So 100 now divided by 2 inches will give me 50 magnification. Now, why would you want to magnify less? Well, because when you magnify less, you see more of the view. If you magnify more, you see less of the view. So let's say with more magnification, you only see a tiny part of the moon. If you want to see a bigger part of the moon, you magnify less. In fact, that's the first error most people make. When you look through a magnification that is very high, you don't see anything because there's nothing there. It's extremely difficult to point your telescope with a high magnification. You need to have a very low magnification. Now let me show you something here. And okay. So let's take a look here. All right, so this is good. All right, like this as an example. So what you expect to see through your telescope is something like this. You go, oh my God, this is a fantastic image, right? You can see little tiny details, but this is not what you see. This is an image that was produced from this image. This is what you're going to see. So what you're looking at is the actual view through the Earth's atmosphere at the moon with high magnification eyepiece. So very short focal length eyepiece. Now, if you see the moon like that, you go, oh my God, what's going on? This is called seeing, and we'll talk about seeing next time. Seeing is the turbulence in the Earth's atmosphere. Why don't we see the turbulence? You do see the turbulence. Turbulence is why the stars blink. If you go to space, stars don't blink. Stars blink because we're on Earth. So if you're in space, there is no blinking star, right? They don't blink at all. So here, this is what you expect to see. And you have to have patience. When you look through a telescope, You take your time. Like you look at this baby here, and you wait for moments of good seeing. So let's see when the moments of good seeings are. Look at these craters here. You see these little tiny craters? Now wait till they get sharp. See, they get sharp, they get fuzzy. They get sharp, they get fuzzy. So you have to have patience. High magnification, extremely difficult to use. That's why when you start with a telescope, you want to use low magnification. That's the most pleasurable way to look through a telescope. Low magnification, not a high magnification, very low magnification. And then you magnify a little more, a little more, a little more. All right. I was going to erase this if you guys are done with this. I kind of like to erase this.
1 second, please.
No worries. See, like this telescope I have, it's like 2 telescopes, right? See, it's like 2 telescopes. This one here is a refracting telescope on top. And this one only magnifies 6 times. That's it, 6 times. And it's called a finder scope. You have to find it first. Don't forget about finding it. So whatever you look at, you gotta find it first. So this is a finder telescope. And it's got a little crosshair, like a gun. You know, gun sight has a little crosshair. And so through there, you gotta find the object. Once you find it, then you look through the big telescope to magnify it.
Professor,
Yes.
on that equation with 100 divided by 2 inches, how do we come up with the 2 to get to 50? Because I know that was what Linda said. You said we need what size lens?
She just thought about this is the way I think her brain worked. I'm not sure exactly, but if you divide it by 2, you get 50. If you divide it by 1, you get 100, right? If you divide it by half, you get 200. So she just figured it out in her head, that's all.
Divided by, if you divide 100 by half, you get 200?
That's right. Like as an example, how many 50 cents are there in $100 bill?
Okay.
You see?
200, yeah.
250 cents in $100 bill, right? Now, how many $2 are there in $100? 50 $200 bills. You see? It was a time when we just talked about money. Money is the thing that everybody gets. You know, if I say an example of money, no problem. If I say focal length of a telescope, oh my God. Money, no biggie. I remember there was a teacher that I took in school, and he was talking about grams of drugs, like cocaine or something. Everybody knew that, right? So when he talked about it, he used those examples back then in the 70s, you know. Weird times, 1970s. Yeah. Of course, none of you guys remember 1970s. You weren't born yet. Very strange times. You know, I tried to stay away from all that stuff. But I had a friend, and she got cocaine through the mail from her father. Her father was a lawyer and sent her daughter, who was like 21 years old, cocaine through the mail. You know why? Because back then in the 70s, they used to think cocaine is nothing. It's not, you know, it's a healthy drugs. Back then, right? In fact, it's not.
Yeah, even the 80s, it wasn't really stigmatized.
Right, but it is not good stuff at all. It ruins your brain, basically. It kills brain cells.
Yep.
And other stuff. It ruins your nose too, right? Anyway.
A hole in everything.
I'm sorry?
I think you can rot your inside of your
Lungs, everything, yeah.
like it rots the inside of your I don't know.
Nasal passages.
Yes.
Yeah, thank you.
Like cartilage and stuff. Yeah.
That's right, yeah, that's true. All right, so now we talked about refracting telescopes, so that's lenses. So how many lenses minimum do you need to make a refracting telescope?
2.
I can see somebody's fingers. 2, that's right. Okay. Now reflecting telescope. Reflecting telescopes. Reflecting telescopes, right? That's just it. Reflecting means mirrors. Remember, we have convex and concave. Just to remind you, this is concave. This is a mirror I use to check my eyes out. There's something in my eye. Is a concave. It caves inward like that. This is a concave shape. Caves inward, right? All right. So in a reflecting telescope, you have a mirror. So this is a mirror for a telescope. Now, let me see if I can tilt it for you. It just reflects the light now. This job is to reflect the light. See if I can show you the camera that is making this image. There's the camera. Right, there is a camera. Now, the surface of this glass is aluminized. That means there's a very, very thin layer of aluminum deposited on top of this glass to make it reflective. They used to use silver, but silver oxidizes, and aluminum takes much longer to oxidize. They put another clear layer on top of it to stop it from oxidizing too. All right, so let's have a mirror that looks like this. It's a nice round mirror. If you look at it from the edge, what does it look like? From the edge, it looks something like this. Look, from the edge, looks like this, right? From the front, the edge. So now, if I look at it from the edge, it looks like this. Looks like that. So now, the light comes from the front. So there's a light coming from the moon, and it reflects it back. And it comes to a focus in front of the mirror. In the lens, it was behind the lens. Here it's in the front. So here's the focus point here. Focus point, focal point, whatever you want to call it. Focal point, focus point are the same thing. All right, so now we have an image there. Now what do we do with the image? Well, we got to put an eyepiece here. If you want to look, eyepiece, and your eyeball. There is your eyeball looking through the lens. What's the problem here? Big problem. The big problem comes around because with the eyeball, there goes a head. Let's not forget the head. So here's somebody's head now. Right, if the head is there, now the light never reaches the mirror. The light was coming from over there, remember? It just hits this guy's back of this guy's head. So it never even comes through. You see what the problem is now? All right, so Sir Isaac Newton, 350 years ago, he fixed this problem. The kind of telescope that he made is called the Newtonian telescope. So this Newtonian telescope solves this problem with a head. So he gets the head out of the telescope tube in front of the mirror. You don't need to have somebody's head. All right, so I want to get rid of this guy's head. If there's no head, I'm going to take the eyepiece out too. Now I'm going to do a little bit of engineering here. Let's see. He
Is that a
introduced,
Newtonian telescope?
yeah, I'm going to write it down for you. So now in this Newtonian telescope, what he did, he said, why don't we put a flat mirror here? So he introduced a flat mirror. Now this flat mirror is held in the middle of a tube by wires. So you have wires holding it. The wires are called spider. If you ever get into making telescopes, it's just held together by these wires called spider. And so in the middle of the tube, there hangs a flat mirror. So this is a flat, and they call this the secondary mirror. So you have an objective primary mirror, and you also have a secondary mirror. So this is called an objective primary mirror.
Did they not have refractive telescopes?
I'm sorry. No, they still use it.
No, I mean then.
Then they still used it
Oh,
because the reflectors were just beginning and they were, not as good because of the way they had to see. They didn't have this aluminizing on the surface of the mirrors. They had to, they didn't even have silvering. Mirrors back then were just metal, and you polished this metal until it was very shiny. And so it rusted every year. So you had to make a new mirror every year from your old mirror. So your old mirror had to be polished every year because it would rust. Right? They didn't have the material science that we have now. So back then, the reflectors were great because they had no chromatic aberration. They give you perfect image, but they only lasted for so long because they would rust. All right, now what happens? Now the light hits this flat. So the light hits the flat, bounces off the flat, comes to the edge. Your image is here. Outside of the tube. And so let me put some arrows here. And you put your eyeball here. And we call this the Newtonian telescope. Newtonian.
I have a question.
Yes, please.
In this case, do you not need an eyepiece where your eye goes?
Yes, you do. Thank you.
You do?
Yes, you do. Yeah, you do. There's no difference. You just brings the image to a focus, right? There's your image. This is the focus point, right? So same thing. You still need an eyepiece. An eyepiece. An eyepiece, and I gotta erase that to put somebody's eyeball, I guess. I want to make it nice for you, so I'll put somebody's eyeball here. All right. It's too bad. I should have given a whole bunch of points today at the board. I don't see you guys, so I don't know who's talking.
I have a question.
Yes, please.
Is the flat mirror placed at the focal point, or is it placed a
Before
little
the focal point, right? Before. It's put here. This is the focal point over here, right? And so you put it like a few inches, depending on how big your tube of the telescope is, right? So you give it extra inches here. You give it extra room so that it focuses outside of the telescope tube. You have to bring the image out. Remember, otherwise you put your head in the front, right? It's like you got to bring the image outside of the tube so you can inspect it. Otherwise, you can't inspect it. That's the problem. All right, so here we have the eyepiece. Eyepiece. And here I'm going to say flat secondary mirror. So to make a Newtonian telescope, how many mirrors do you need?
1.
2.
Three.
You need 2 mirrors and 1 lens. Eyepiece is a lens, so you need 1 mirror, the objective primary mirror, you need a flat secondary mirror, and that's it. 2 mirrors in a Newtonian telescope. You see that?
Hmm.
Yeah, 2 mirrors in a Newtonian telescope. All right. But there's still a problem here with the Newtonian telescope. What do you think the problem is?
Focusing.
No, focusing is fine. You just move the eyepiece up and down a little bit, until you get a nice focus for your eye. But there's another problem. The image is getting like here. With a refractor, what am I doing? With a refractor, I go, I see it, right? Ahoy, Captain
Pointing-
Land, right? You see
Pointing it at a place where you want it.
No,
Focusing.
no. It's just that the image is in front of the objective. So let's say you have a mirror this big. It reflects the light upward, right? You got to be up in the air. If the focus is 40 feet, you got to be 40 feet up in the air. How do you reach focus? You got to climb a ladder. So, excuse me, you climb a ladder in the wintertime in Europe 350 years ago. Now what happens? You fall down and you kill yourself. That's what happens. And it's very long too. So since then, we built space telescopes and we built all kinds of telescopes.
Oh, this is the one that they had to build the big the big thing to climb up to look, that you said how that it was magical that they had to build the large crane type thing to separate. Is this what you?
That was just a fancy refracting telescope. If the focal length of the refracting lens is very, very long, you know, extremely long, like, I don't know, like 60 feet, really long, then at that point, the chromatic aberration becomes minimal. So the color goes away, your images get much sharper. That's why they did it with lenses. But this replaced that. This replaced the fact that this doesn't have the light going through the mirror. It reflects off the surface. So there is no chromatic aberration here. So this
has, to climb up high, you have to climb up high, as in the eyepiece will be far above the primary mirror.
Right. So no chromatic aberration in reflector. In reflectors, that's a huge advantage. Reflector, there's no chromatic aberration because there's no medium. The light doesn't go through anything, right? It just reflects off the surface. So no problem with chromatic aberration now, right? So you're good. But you just have to go, again, the end of the tube is 10 feet up. You got to reach 10 feet. Even today, there are some people, they call them amateur astronomers. Amateur astronomers, like, they take their Newtonian telescopes because they're so inexpensive. They buy it and they go to the desert and they have to reach the eyepiece. To reach the eyepiece, they need, you know, like a little ladder. So they go on top of the ladder and they go, okay, let me go on top of there to look through. And they still fall down. It's not okay. They fall. If the telescope has a 50 feet long focal length, they got to go 50 feet up in the air. Even the King of England fell off a telescope. All right, it's an old story. I think he was up there partying, drinking and all that. There were prostitutes on the ladder and they made him fall and he broke his arm. So it's very dangerous. So for that reason, they said two things. Let's bring the focal point in a reflecting telescope behind the objective, like over here. So we want to focus over here. How do you get the light over here? So your eye is back here. That'll be awesome. And let's make this shorter so it can be more compact. Then we can, we can have a much smaller dome for the observatory. Otherwise, for Newtonian telescope, you have to have a giant domes, huge domes, right? Nowadays, you have a space telescope. You have to put it in a space shuttle or in some kind of rocket. You don't have room for a Newtonian telescope. You got to make them shorter. So the way you do that, you make something called a Cassegrain telescope. So this telescope is called a Cassegrain telescope, and it uses both concave and convex mirrors, and it's very short. Look how short it is. It's like 10 inches. This telescope really is got a focal length of 50 inches. So the focal length is fantastic. You can magnify a lot with any eyepiece. So it's awesome. But how do we do that?
How much is a telescope like what you were just holding?
Oh, like less than $500. You buy it, used. I told you telescopes are much cheaper now. So you get a mirror, right? You get a mirror, and you put a hole in it, like this. You see, there's a hole here. You drill a hole in there. There's special drills, they drill it right into the glass, and eventually they illuminize the surface. You have to ground and polish it. You grind glass by putting abrasives between two mirrors. So if you have like two mirrors, you put some abrasives, and as you grind them, the ones on top, right, becomes concave. The one on the bottom becomes convex. That's how the shapes are formed, right? So you get two pieces of flat glass, like that. And you get some water. You put abrasive here. Abrasive is like what you have on sandpaper, except it's not paper, it's loose, abrasive. So you put the abrasive here, and you go back and forth. You grind them like this. You go back and forth, back and forth. So eventually the one on top becomes concave. The one on the bottom becomes convex. Like that. That's how they shape it. Once you grind them to shape, then you polish it. You polish it with a pitch. You've seen pitch from the trees, it's like that gummy stuff, kind of soft, gummy stuff, hard as like plastic, Then you got to polish it with that to make it really smooth. Because glass is liquid. So when you use this polishing pitch, the glass melts and makes a beautiful, smooth surface to within something like a billionth of an inch accuracy. Incredibly, the most accurate surface ever made by man is in the mirror of the Space Telescope. It's like incredibly accurate.
Can I ask a question?
Of course. Is that Mina?
Please don't erase it. Could you please don't erase it? How we calculate the focal length of this telescope?
Well, you calculate the focal length of this telescope by removing everything here and then measuring it. So the distance between the mirror, like here in the center, when the image is focused, that's the focal length. So you don't put it inside the telescope to measure it. You measure it outside the telescope. So you don't put it in the tube. You just, like you see where the light is focused, and that's how you measure it. Like that. Okay, so there is the focus point. You measure that distance.
But the focus point is not here. It's on the top.
Focus point can be anywhere. You measure it before you put it in the telescope, right? So you shine light on it and see how long it takes the light to focus. Like let's say this mirror.
But for this one, the focus
point for any mirror. In other words, it doesn't matter. You take it out, now you have a mirror. So like this mirror here is outside the tube of the telescope. So you take it out and you measure it before you put it in the telescope. Do you follow what I'm saying?
Yes, I thought that we're gonna add two.
No. No, there's no addition. This is a flat, right? This second one is flat. It's a flat secondary mirror. So if it's flat, it doesn't add to the focal length.
Okay.
It's set. Yeah.
Thank you.
What is the name in?
Oh, I gotta draw the whole thing for you. Give me a second. I'll give you a name. It's called Cassegrain, but I'll give you a name. All right.
I'm just talking about of the large mirror.
Large mirror.
The objective.
It's called an objective mirror. That's it. Yeah. It's just
okay.
Yeah. That's
all right. Thank you.
A name. Yeah. It's nothing fancy.
Okay.
So now you see, I got a hole in here, right? So the light can go right through the hole here. So first thing you got to do is to drill a hole. So we draw a hole, and see, I've lost all my pens now. So many pens here. Okay, so now let's see if I get a mirror like that. I drill a hole in the center. So now I got a hole. There's a hole in the mirror. So this is the primary mirror. All right, so the primary mirror I already got, and it looks just like this. From the front, it looks like this. It's got a hole in the center. From the edge, remember, it looks like this from the edge. So now I'm going to draw it from the edge. So here we have the edge of the mirror. Let me draw it first. Okay, now we put a hole in here, right? So we put a hole. Hole. Right. So here's our mirror with a hole in there from the side. This is side view, right? So now the light comes in and hits the primary mirror. Then reflects. Now, here, when the light reflects, we need one more mirror. But this time, we're going to use a concave mirror. So now we want a mirror to be convex. This is a concave mirror. Now we want another convex mirror that looks like that. You've seen these mirrors, right? They look this giant mirror that look like that. You know where you see them? At the corner of like 7-Eleven. So what do they use it for? They put it in the corner of the 7-Eleven, very corner. And then they can see who is at the alcohol department. They don't want anybody stealing alcohol, right? Where all the beer is, you'll find it. So what does that do? It appears that the image is far away, right? If you look in there, you can see the entire store inside of one of these convex mirrors, right? So these convex mirrors are only good. You've had them in your car too, like some of the cars have convex mirrors, so you can see the whole road. Like they have it on the right side of the mirror so that you don't hit somebody's car, like when you want to change lanes. Oh, okay. So normally your right side mirror is a concave. Your left side is concave, your right side is probably convex mirror, so you can see bigger. So we're going to put one of those mirrors here now. So I'm going to put one of these convex mirrors here. Now, this actually adds to the focal length because, remember, you look at one of these convex mirrors, you see your face way out there. You go, oh, I look like I'm 20 feet away. That's exactly the point here. In other words, the image appears to be far away. And so it adds to the focal length, makes your focal length much longer. And then the image goes to the center, like back here. So we accomplished what we wanted. We did two things. We brought the focal plane, or we brought the focal point behind objective mirror. That was one of the things we wanted to do. We didn't want to fall off the ladder. Objective mirror. So that's the one thing we wanted to do. We don't want to die climbing ladders in the wintertime in Europe, so we did that. So the focal point is behind the objective mirror, right behind this guy here, primary mirror. And now we also made it compact. So we compact, very tiny. Now we can shove it into the cargo bay of the space shuttle as an example. Here's where we put our eyepiece now. Here's where we put our eyeball, just like a normal refracting telescope. That's it. Now these are called Cassegrain as a generic name. Cassegrain. Cassegrain. So these are called Cassegrain telescopes. I guess you guys can't really see this, but here and here now there is a mirror back here. You can't see it because it's on the other side. It's smack in the middle. So light comes in, hits the big mirror back there. You can see the big mirror. Now the reflection of the small mirror is also in the big mirror. So if you look at the big mirror, it's got a little something in the center. Let's see if I can point at it. You see, this is the second mirror here. And so that one reflects the back. It comes through the hole in the back of the telescope here. So now you want to put your eyepiece here. So I'm going to stick my eyepiece here, and I have a reflecting telescope now. See how tiny and compact it is? There you go. Now I look at it like this. like that.
I have a question.
Yeah.
So you said that the little like piece on top of that is an objective telescope that you can use to
A
find.
refracting telescope, not objective telescope. Objective is just either a big mirror or a big lens. That's the objective.
Okay.
The one that collects the light is called objective. It collects the light. Its job is to collect the light and brings it to a focus.
Gotcha.
Oh, is that photo the whole of the primary mirror? And then the next ones are called primary mirror. Is that it broken up? Is that
I'm sorry, broken up?
I'm sorry, are the sketch on the bottom that says primary mirror,
Right. This is a primary mirror, right? This
right?
is a primary
Is
mirror.
that a breakdown of or a side view of the primary mirror front face?
Yeah, this is a side view of this guy here, right? There's got a hole in the center.
Uh-huh.
You have to put a hole in the center here, right?
So that is this. Okay. Thank
So
you.
this is a secondary convex mirror. The ones that you find at 7-Eleven. Now we made it compact. We also brought the light behind the objective, just like a refractor. So now you just look at it like this, like that. Easy. Easy peasy. So
And
yeah,
what is compact cosogram? What is that?
compact.
The compact and cosogram?
Cassegrain is the name. Is the name of the system. Compact is just compact. It's compact. So they're compact, and the focal point is behind the objective mirror. Those are the two advantages. One, focal point is behind the objective mirror back here. That's what we try to do. Two is compact. It's short, very short. Those are the advantages of the Cassegrain telescopes. There are different names, you know, like some of them are called Schmidt Cassegrains. Those are the German design, like Bernhard Schmidt. And then there was Richie Chrétien, and Mr. Chrétien and Mr. Ritchie made their own design. And then we had Maksutov, Cassegrains. That's a Russian design. And we had.
So this is a drawing of a Cassegrain telescope.
This is a drawing of a generic Cassegrain telescope, because you can't really see the curves on the surface of the mirrors. We have different curves on them. That's what the differences are between like a Ritchie Chrétien and this is a classical Cassegrain.
Thank you.
You're welcome. Classical Cassegrain is good for looking at the planets and stuff.
And sorry, compact is the size of the Cassegrain telescope?
Compact is the size, that's right. It's small, right? So you can put it in the cargo bay of the space shuttle.
So I'll say Cassegrain telescope, compact size telescope.
They're compact. Also, the focal point is behind it. These are all reflectors, right? They're all use mirrors. Refractors are also very long. Newtonians are very long. Cassegrains are short.
And
Is the-
focal point is behind it.
Now you make your dome much smaller, right? Much, much, much smaller domes. Let's see.
Is the primary concave mirror still referred to as an objective mirror?
The concave, yes,
It's still called objective. Okay,
correct, yes.
thank you.
Whatever collects the light and brings it to a focus is called the objective mirror, yeah. Absolutely mundo, yes. What happened to my image here? Okay, let me just share a couple of things before I say goodbye to you guys. Let's see. So here is using Newtonian mirror. You see how this eyepiece is at the end? Light comes in, hits the mirror. This mirror is very close to the ground. Eyepiece is up in the air. So this thing is 20 feet tall. This guy is got to go 20 feet up in the air to reach the eyepiece, right? That's a bummer, right? Not very good. This is what the Newtonian telescope looks like. The eyepiece is on the side. This is a focuser. The job of the focuser is move the eyepiece here, in and out, so it focuses for you. This is a finder scope. Finder scopes are always refracting telescope, lens in the front, lens in the back. Simple. This is the spider that I told you about. The flat is mounted with these little wires. So the mirror is sitting here, it reflects the light all the way here. Then we have the Cassegrain. Light comes in, hits the primary mirror, bounces, hits the secondary mirror, bounces, goes through the hole, focuses back here. This is where you put your eyepiece and your eyeball. Right. Here's a Schmidt Cassegrain. If you see catadioptric, it means that it's lens and a mirror. Too fancy. So there's a lens in the front. The second mirror is mounted in the lens in the front, and there's a mirror. So there's a mirror and a lens, and oh my God, there's a hole here. The light goes through here. The eyepiece is back here. It's kind of a, complex system. That's what it looks like. There's a Cassegrain for you. That's what the Cassegrain optical path looks like. That's what they look like in real life. Mine is just like that one that I just showed you, except mine is orange and pretty. And then this is what you see when you look through it. Not this. This picture here was made from this picture here. So what they do is, this is a video, and videos are 30 frames per second here most of the time. So this is like 5 seconds. There's 150 frames. They choose the sharpest images, and then they stack them on top of each other, and they make this image from that. So this image is the same as the other image. The other one is a video. You take the video image and you turn it into a fantastically sharp single image. Yeah, pretty fancy.
Do you think reflective or refractory is one is better than the other for viewing images?
If you're going to be moving the telescope a lot, like putting your car going to the desert, then reflectors are kind of like move around a little bit. The big mirrors move around. So refractors, the lenses are sitting there very tightly. They don't move at all. So they'd be better for transportation.
I see. Thank you.
You're welcome. All right. Anybody has any questions here? Let me see if I have any questions here. Yeah, the sun don't blink. The stars don't blink, right? So the stars don't blink at all. If you go to space, everything's stationary. In fact, Yuri Gagarin was the first Russian guy to go to space. When he got to space, first thing he said was, "Oh my God, the sun is so bright. The sun is twice as bright in space." So the atmosphere of the Earth absorbs half the sunlight, which is pretty impressive. And then he also said, "Look, the stars are not blinking. The stars are stationary. The only reason they blink is because the light of the star has to go through the atmosphere, and the atmosphere is turbulent. So as if the atmosphere moves around, it becomes a blinking star." What do they call it? Blinking star, right? What does that song say?
Twinkling.
Twinkling. Thank you. Twinkling. Thank you. Yeah, twinkling star.
I have
You guys are so helpful.
I have a question, but it's just slightly off topic.
Okay.
Assuming that you only have a concave mirror, after the light reaches a focal point, would it essentially like flip the image of what it's viewing?
You mean it's upside down?
Yes.
Yes. Yes. All the objects are upside down in all the telescopes except for the Cassegrain. Cassegrain will be left to right, I believe. But here's the thing. In space, there's no upside down. Like, which side of the moon is up, which side of the moon is down?
That's a good point.
Yeah. So they don't care about up and down in space.